So happy to be here. Last time I spoke at Palm Desert was in February 2020 at an Are We Alone seminar, and I think we all know what happened very shortly after that. I'm so glad to be here. I think I recognize some of you from last time. And what has changed since 2020, of course, is the launch of the James Webb Space Telescope in Christmas 2021. And in that short period of time, we have just explosively expanded our knowledge of exoplanetary atmospheres. So what I'm going to do with this talk a little bit is to orient you to exoplanets, how we detect them, how we can characterize their atmospheres, what James Webb has already taught us, and then where we're going. What is the pathway to habitable and maybe even inhabited planets if they're out there? Okay. Whoop. It's not, oh, it's a little slow there. Okay, and this stopped working. If you could fix that, thanks. Okay, so first of all, our place in space. So we're on planet Earth. We're in the solar system, our lovely solar system, with 8, or depends on how you count it, controversial planets. We're in the Milky Way galaxy, which is itself in the local group of a hodgepodge of galaxies. Milky Way is one of the 2 largest ones, and we're embedded in supercluster of galaxies. There are, sorry, there's quite a long delay. 100 billion stars in the galaxy. And more than that in the galaxies in the observable universe. And so that's almost 10 to the 23 stars. So that's 10 with 23 zeros, or 1 with 23 zeros after it. But the closest galaxy is really far away. And so when we're looking for exoplanets, we're really talking about planets in our galaxy, and especially nearby in our galaxy. So to look at planets that have been discovered so far, we are currently in an age of planet discovery. The very first planet around a sun-like star was found in 1995. You might notice a big jump in this graph around 2009. That is when the Kepler spacecraft launched and found thousands and thousands of planets through what we call the transit method. I'll talk about that in a little bit. And that has only built up. In 2018, the Transiting Exoplanet Survey satellite launched and opened up the solar neighborhood to transiting exoplanets. And so currently there are 5,300 confirmed exoplanets, and thousands of more we think are there and have not yet confirmed. How do we find exoplanets? There are a few main methods. So one is called the radial velocity method. This is looking for the reflex motion of the star as the planet orbits it. So we think of planets orbiting stars, but really the star and the planet are orbiting their common center of mass. The star is a lot more massive than the planet, and so it just makes a little bit of a wobble as it orbits the center of mass. But with very sensitive instruments, we can detect that slight wobble through what's called the Doppler effect, which is just the idea that as the star is coming towards us, the light gets a little bit bluer. As it's going away, it gets a little bit redder. And this is how allowed us to discover the first exoplanets around sun-like stars. Another and the most prolific method right now is called the transit method. And in this method, we're looking for the miniature eclipse as the planet passes in front of the star. And when that happens, a little bit of the light from the star is blocked. And this happens periodically because the planet is going around the star in an orbit. And that allows us to get the period of the planet, and the extent of the dip gets us the size of the planet. And there are a few others. One obvious one is direct imaging, taking pictures of it. This is really difficult, especially for Earth-like planets, just because of how much the star outshines the planet. And then finally, there's something called microlensing, and this is looking for the fact that planets kind of warp the space around them. And when we have a planet close to us, maybe it's even not attached to a star, passes in front of a background star, we get a dip. Unfortunately, we can never ever follow that planet up again. So it gets a statistical view. By far, the most common method is the transit method in terms of its success. And here's a bit of a video of that. So this video isn't working very well. Sorry about that. But what you're seeing here is that the small planet transits, it creates a small dip in the brightness of the star with time. The larger planet passes, and it creates a larger dip in the brightness of the star. And so, importantly, we can't see the planets. We're looking and inferring the existence of the planets from this effect on the brightness of the star. Not all planets transit, only the systems that just happen to be aligned so that their orbits are edge-on from our perspective. So we're finding all the planets that are out there through the transit method. And we have a limited view of which areas of the sky we can see. So Kepler looked at one place in the sky, in the summer triangle between Cygnus and Lyra, the constellations, and it just stared at that place. Why? Well, because the transits only happen every so often. The Earth, if we were looking at it as a transiting planet somewhere else in the universe, would only transit once per year. And so you don't want to miss that, meaning you have to look at the same place for a long time. And Kepler looked at that place. It happened to be just above the galactic plane, and it cataloged these thousands and thousands of potential planets. The Transiting Exoplanet Survey satellite TESS had a different strategy. The strategy is to look nearby. And kind of go and look at various places in the sky for 60 days, a few months, couple months, and then move to a different part of the sky. This limits the period of the planet we can find, but it gives us an idea of what's actually in our neighborhood instead of just this pencil beam through the galaxy. And so if you bear with me, we have a video that may or may not show. But what you're seeing here is an animation of the TESS satellite surveying the entire sky. And it has these footprints. It's building up this spherical shell around us and finding planets that transit. This limitation I told you about, it's only looking at each place for a given period of time, still allows us to find planets that have short period orbits and of less than 60 days or so. And importantly, some of those planets reside close to their stars, and those stars are dimmer than the sun. And so some of them are actually in their star's habitable zone or temperate zone, where you could imagine liquid water existing. Of course, most of them are hot. What kind of planets are we finding? This is a demonstration of the planets that we have found through these different methods. And one thing to notice is it's really, really easy to find large, massive planets close to their stars. We're finding all of those. It's much harder to find small planets far from their stars. And so this apparent absence of planets around Earth is not a real effect. It is simply a reflection of, one, our limited technology so far, and two, the limited amount of time we've been looking, right? If we are trying to find a true Earth twin, it only transits once per year. And we haven't been looking very many years with the right technology. That's going to change. On the right here, you see a histogram showing the relative distribution of the sizes of the planets. Partly this reflects the intrinsic commonness of those planets, but partly it's also kind of tilted towards the fact that large planets are easier to find. What's interesting is that there is this class of planet in between the size of the Earth and the size of Neptune and Uranus in our solar system, and those are called super-Earths. It turns out when you correct for the biases, super-Earths are the most common type of planet in the galaxy. And we don't have one in our solar system. So we're going to start characterizing those and learning about how different they are. This infographic from NASA gives us a bit of a description of the different classes of planet you see here. Our gas giants like Jupiter and Saturn, Neptune-like planets like our ice giants, Uranus and Neptune, terrestrial planets, which can be like Earth, but remember Venus, which has a hellish surface, sulfuric acid clouds, that's also an Earth-sized planet. And so, Earth size doesn't necessarily mean Earth-like, but it's made of rocks. It doesn't have a very substantial hydrogen and helium atmosphere. Super Earths kind of lie in between. They may be rocky, or they may possess a hydrogen-helium envelope, depending on their exact size. And so how are they different geologically? How are they different in their atmospheres? A lot of people are working with computational models to try to figure it out, but ultimately we're only going to learn from direct observations. Now, I know a lot of you are thinking, I really want to find those Earth-like planets, and so do I, and we all often think of, where are the rocky planets that are just the right distance from their star to potentially have surface liquid water. We have this tool called habitable zone. Sometimes people don't like the term habitable zone, but you can call it liquid water zone or whatever. But it's the idea that if you're too close, if you had oceans, it would boil off, the water vapor would go into the atmosphere and you'd lose it. That probably happened to Venus. If you're too far away, you're cold, and your water freezes out, your ocean freezes, you turn into a snowball. Importantly, being in the habitable zone is not enough to be habitable. The moon, of course, is in the habitable zone. It's too small to hold on to an atmosphere. And we think that we need the right kind of atmosphere and the right geochemical cycles in order to maintain habitability. Okay, well, we had this working before, so, oh well. If you want to just use it as the laser now. Yeah, okay, thanks. Everything always works when you practice and then it stops working. And so importantly, another thing is, even if the planet's habitable, it has surface liquid water, doesn't necessarily mean it's habitable for you. If you went there, the Earth for most of its history, half of its history, as you heard from Dr. Lyons last week, didn't have oxygen in its atmosphere. And so we couldn't have lived on the Earth for half its history. We might not be able to survive on planets even if they're habitable. So the habitable zone changes depending on what kind of star we're orbiting. There's a very intriguing system called the TRAPPIST-1 system. It's a compact system of rocky exoplanets, a few of which lie within this liquid water zone, depending on how you calculate it. Importantly, this TRAPPIST star is about 8% the mass of the sun and less than 1% its luminosity. The habitable zone is very close, and so if you look at the entire planetary system, it fits well within the orbit of Mercury. This system is going to be very important later on because it's one of the primary targets of the James Webb Space Telescope. If we add up all the planets we found in this temperate zone, depending on how you count, it's a couple dozen, maybe a little bit more if you're optimistic, depending on how you cut on the radius of the planet and their actual insolation. That is the amount of light they're receiving. So these are the ones we know so far. I'm going to come back to that later because they're not the ones that we know have any atmospheric information about yet. This is their location in the sky. You can see this is an effect of Kepler. A lot of them are in that field of view of the Kepler spacecraft just because of an observational bias. And there are, of course, we think intrinsically just as many scattered out through the sky. And the fact that you don't see as many in other places in the sky is simply a reflection of this observational bias. We had Kepler look at one part of the sky for a long, long time. So the planets we really are getting information from about now that are going to teach us how to characterize these temperate planets potentially are actually the hot Jupiter planets, these hot planets that are close to their star. Just for the same reason they're easier to find, they're also easier to characterize. It's also easier to learn about their atmospheres. And so we're going to do this, and we have already been doing this with the James Webb Space Telescope. It has a 6.5 meter aperture, that is its collecting area. It's got a gold plating to help it collect infrared radiation. This is substantially larger than the Hubble Space Telescope, so it can collect a lot of photons. It can give us more signal to noise. It's got a sensitivity from optical wavelengths, that is the wavelengths we see, kind of red colors, all the way through the infrared, into the mid-infrared. In order to get those infrared wavelengths, it's actively cooled. That is, it has coolant on board to cool it down to 50 Kelvin. That is negative 370 Fahrenheit. It's stationed at the Earth-Sun L2 point, which is basically a point in space outside the orbit of Earth, where both Earth and the Sun are contributing gravitationally. And this keeps Webb away from a lot of interference that could happen from basically having Earth in the frame. It also helps it keep cool. And it has several instruments that allow us to do what's called spectroscopy of exoplanet atmospheres, among other things. And so how do we characterize these exoplanetary atmospheres? Well, there are a few methods. One is we look at the transit, and we look at the wavelength-dependent dip in the light. That is, the dip has different magnitude depending on the wavelength. And that makes the planet appear different sizes. I'll show a video of this a bit, but of course, the video might not work out so well. Another thing we can do for hot planets is as they cross behind the star, we lose their light. And so by looking at the planet plus the star, and then looking at just the star and subtracting it out, we can get the light from the infrared light from the planet. And that can give us some information about the atmosphere as well. So I really hope this video works. But what this is showing is that the planet has different molecules in the atmosphere which absorb light differently. And that means at different wavelengths, this transit depth, greatly exaggerated here, is different. Okay, and this can allow us to infer the existence of molecules in those exoplanetary atmospheres. It's just so smooth on my computer versus this. Okay. So here is the electromagnetic spectrum. You probably know we see a very, very small part of it. Those are the visible wavelengths. The Webb telescope starts here at about 600 nanometers and goes well into the infrared range. The infrared is very important because these very important molecules in exoplanetary atmospheres selectively absorb certain wavelengths of this infrared light. They absorb those photons and they go through what are called transitions. They vibrate, or they rotate, or they translate. They do different things. And we can understand their properties on the lab on Earth, understand which wavelengths they selectively absorb, and then search for those patterns in distant planets to understand their composition. And so I'm hoping that this works a bit. So this this says detection of biosignatures, but it really applies to detection of any molecule. What we do is we take the light from the star and put it through, this is a prism, but it's really a diffraction grating on the telescope. We get this wavelength. We do it when the planet passes in front, and then we subtract the light from the star from the light of the planet plus the star, and that gives us the unique signature of the planet. And so using this method, we can match these patterns to the patterns we know from laboratory measurements on Earth. And so here it's showing that we find evidence of water and methane in that exoplanet atmosphere. And so before Webb, we had this data. Now, I want to make some important observation here. These are data points on top of models. That is, we put things in a computer and guess what it looks like. The actual data points are the measurements. And so you can see here in the infrared, these are 2 data points. Everything else here is a guess. Okay? And so we have these 2 data points from the Spitzer telescope. And we're very limited in the size of the error bars from both Spitzer and Hubble. Now what happens when we use the powerful Webb telescope with its much larger diameter, with its ability to collect a lot more photons, with its active cooling, giving us access to more refined infrared data? All of a sudden, we can detect molecules with much greater precision. So this is just 6.4 hours of observation of a hot giant planet, WASP 96b, finding evidence for a steam atmosphere. So this is water vapor absorption in this hot planet. This planet is screamingly close to its star, half the mass of Jupiter, blown up a bit to 1.2 Jupiter radii. This is not a place we'd find life, but it is a place where we can find molecules, and we can understand the composition of these atmospheres. So this is one of the first. We also, just in the summer of last year, found evidence for carbon dioxide for the first time in exoplanet atmosphere. This is a different planet. This is called WASP 39b, which is a hot Saturn-like planet. Probably doesn't have rings like Saturn does. But this was a very, very amazing find. So this CO2 comes from chemical reactions, chemistry happening in the atmosphere. It's not from volcanoes like we know on Earth. But the fact that we can detect this CO2 is really important because it's something we will look for on terrestrial planets like Earth. Earth has CO2, Venus, and Mars. So that's not the only spectrum we got of WASP 39b. We have this amazing collection of data from the planet. So we found, using the different instruments on Webb, water, evidence for water, carbon monoxide, carbon dioxide, of course, as we put, and very importantly, something really, really interesting, sulfur dioxide. Okay, so we're seeing multiple molecules in this hot Saturn planet. That's telling us about the chemistry that's happening, not just the chemistry that's happening, it's deep layers that's being brought up by mixing, but chemistry that's happening due to photochemical reactions with light, ultraviolet light from the star, and the molecules that exist in its atmosphere, transforming them into different molecules. And so here's a close-in of this sulfur dioxide detection. And this is just amazing. This is the first detection of SO2 and the first detection of photochemistry on an exoplanet. And so I walk you through a little bit of how this works. So you have an ultraviolet photon. It splits apart water and reacts with hydrogen sulfide, eventually oxidizing this hydrogen sulfide through several sequence of reactions to sulfur dioxide. Okay, and importantly, this is not sulfur dioxide from a volcano. This is sulfur dioxide that is forming photochemically in the upper atmosphere of this planet. The first author of this paper that made this discovery is named Shang-Ming Tsai, and he's actually now at UC Riverside. He's working with me as a postdoctoral scholar, but he did this work at the University of Oxford. And so this is just an amazing find. We want to see evidence for photochemistry, of course, in terrestrial planets, but this is the first step on the way. And this discovery was presented in a series of papers in Nature Astronomy and other high-impact journals. All of these scientists are involved. This is just a subset of them, but they were all led by early career researchers, that is, postdoctoral scientists who just received their PhD in the last few years, or students themselves. And some of these quotes are really good. Our work proves this incredible potential of JWST for measuring the clouds and chemistry of faraway worlds. I'm lucky and overjoyed to be a part of this dawn of discovery. All of this stuff, that the expectations that people had for James Webb have just been completely surpassed. That we were worried a little bit about the precision of the instruments. We were worried about the noise, what are called the noise floor. Would we be able to get such good data? And it turns out all those fears were for naught. We actually have data that is better than expected. So those are giant planets, and let's get closer to our terrestrial planets, our rocky planets. This is an exoplanet, rocky exoplanet LHS 475b. It is the closest in radius to Earth planet ever discovered. It's 99% of Earth's radius. It's hot. It's got a 2-day period around its star. Its equilibrium temperature, that is the temperature that we can guess based off of what it's called radiant equilibrium, assuming it's receiving and emitting the same amount of radiation, is 586 Kelvin. So the Earth is 288 Kelvin, to give you an idea. It's hot. It's about 40 light years away. And again, this is the precision of the data that allows us to get this 0.99 Earth radius estimate. So what's in its atmosphere? Well, that we don't quite know yet. If we look at the wavelength dependent data, we have different models for what's in the atmosphere. So one is a carbon dioxide model and one is a methane model. Right now, we don't quite know enough to rule these out completely. It's all consistent with a flat line. There are several possibilities here. One is that it doesn't have an atmosphere, maybe not super surprising. One is that it has high-level aerosols that effectively block us from probing the lower atmosphere where there might be more molecules. And another possibility is it does have an atmosphere and we just need to look at it for longer. And of course, this planet is going to be characterized more. And so if we want to look in, I actually know the first author of this paper. I went to graduate school with him. His name's Jake Lester-Jaeger. He's at Johns Hopkins Applied Physics Laboratory. And you can see that what we do know is that they don't have a hydrogen-helium envelope, because if they did, they'd have these big whopping transit spectral signatures, and we just don't see those. Okay, so we have this much more refined spectrum. And so if we have an atmosphere like Earth's or Venus's or Mars that has a high molecular weight, that is heavier molecules than hydrogen, like nitrogen, then we're going to get much closer to this flat line, and we're going to need more transits in order to rule out an atmosphere. So is James Webb actually taking pictures of planets to find them? And the answer is yes, with an asterisk. So this is a picture that James Webb took that detected or characterized an exoplanet, HIP 65426b, phone number. A lot of stars have phone numbers as their designations, and then we put B there for the first planet we find. It's very creative. But this one is 6 to 12 times the mass of Jupiter. It's 100 astronomical units away from its star, which means 100 times the distance between Earth and the sun. And it's very young, 20 million years old. Young planets are hot. And so why could we find this planet? Well, it's hot, so it's radiating a lot. That makes its signal big. It's far away from the star, so we don't have to compete with the stellar contamination. And that makes it easier to distinguish the planet and the star. Okay, and so yes, James Webb can find these planets by taking a picture, but only if they're hot and far away from their star. But some of these planets that are hot and far away from their star are really interesting. So this is an exoplanet that has just had its emission spectrum characterized. And what we can see here, this is a planet that's 10 to 20 Jupiter masses. It's hot. It's got evidence for chemical disequilibrium. That is, things are mixing in the atmosphere, taking up things from hot lower layers up to cooler higher layers in the atmosphere. It has silicate clouds, so made of rocks, effectively, that are vaporized due to the temperature. And this is the spectrum. And so we've actually, so the folks who characterized this planet found more molecules in a single atmosphere than have ever been found before. Now, this planet is barely a planet. It's at that boundary between a Jupiter, a super Jupiter planet, and what's called a brown dwarf, which is a failed star. So there's a bit of a ways to go to get the smaller, cooler planets. But we're on our way. The next kind of phase, I like to think, is looking at rocky planets that are in the Venus zone. You'll hear a little bit more about the Venus zone from Dr. Stephen Kane, who will give a talk on April 19th. But one system in particular in the Venus zone is very interesting. It's the L9859 system. This was discovered by TESS, the Transiting Exoplanet Survey Telescope, and it's this system of planets that are between the size of, are basically similar to Earth, maybe bigger, and one that's between the size of Mars and Earth. Now, these planets orbit at a distance where the stellar light is a lot more intense than on Earth, but maybe not so far, not so close that their atmospheres would be blown off. They're close to what's called the cosmic shoreline, which is this idea that we have a line in the flux received, that is the light received from the planet, by the planet from the star, and its escape velocity, which is controlled by its mass, its surface gravity. And so we kind of see in our solar system that the worlds that are far above that line do not have atmospheres, and those that are below retain atmospheres. And interestingly enough, these planets kind of straddle that line. And so what we want to do is see, are there atmospheres there? Because if there are atmospheres there, then that is good news for the planets that are further away. M stars, when they're young, are very bright, much brighter than they are now. And so some people think maybe even the temperate ones don't have atmospheres, that they just couldn't have retained them through time. But if we look at these close-in ones, which are easier to characterize, and we find atmospheres, that gives us a green light for the maybe more interesting ones that are further away. So I actually had a student look at this system and use computational models to predict their spectral signatures, which we'll look for in JBIS-T. Her name is Daria Podorodetska, and she published this paper in 2021, doing multiple different simulations, assuming different kinds of compositions that these planets could have, from having a hydrogen-helium envelope, which we don't expect, but it's kind of a null hypothesis, to steam atmospheres, CO2 dominated atmospheres, and something very intriguing, which is an abiotic oxygen atmosphere. How could we get an abiotic oxygen atmosphere, you ask? Well, if the oceans evaporate and we have a lot of H2O, the H2O gets broken apart by stellar photons, and the hydrogen, which is much lighter than the oxygen, escapes. You can end up retaining that oxygen until you overwhelm any sink for that oxygen and maybe have basically an oxygen-rich atmosphere left over, which may be bad news for attributing oxygen as a biosignature. What's beautiful, though, is if those exist, we would find them in the Venus zone first, where we don't expect there to be life. And that would give us a kind of a warning. If we don't find them there, then maybe that's good news for oxygen as a biosignature. And so Daria did simulations of steam atmospheres and CO2-dominated atmospheres, depending on how prevalent clouds and aerosols are on these worlds. James Webb may actually be able to detect an atmosphere in just a few transits. Okay, and this kind of observation is going on now. It's being proposed to be done now. Someone might even have the data. And so she also looked at these abiotic oxygen atmospheres and what their signatures of oxygen and ozone would be. So I'm kind of illuminating a path forward from what we know about exoplanets to what we may be able to find in the near future. Thinking a little bit further ahead, I could talk a little bit about my research, which is involved in these non-habitable planets. I think planets are interesting no matter what, but of course we're interested in the habitable ones and the ones that could have life. I work on a variety of things, interfacing with observers, although my methods are primarily computational. So I model Earth as an exoplanet. Can we improve our models of Earth so that when we look at data taken by interplanetary spacecraft and compare that to the models, is it correct? Can we extrapolate that to exoplanets? What kind of biosignatures can we expect on those exoplanets? And then how does photochemistry, we talked about photochemistry on WASP-39b, how does that differ if you put the Earth around different stars? And it turns out it changes a lot. So methane on our planet is about 1 ppm. For the same amount of production of methane on an exoplanet, you would get 1,000, around an M star, you could get 1,000 ppm methane. Actually makes it a lot easier to find. Now this is hard because astrobiology is an interdisciplinary field. We got to know a lot of questions if we're going to look for life elsewhere. We have to know what we're looking for, what kind of gaseous products we might look for, what kind of surface signatures could exist on an exoplanet, how those things that we just discussed and cataloged could maybe be produced by geological process, by abiotic processes. Could we recognize the difference? That's really important. When we look at an exoplanet, as you saw, we're limited in the quality of data we're going to find. We're very limited in the quality of data we're going to find. We're pretty far away from being able to take a picture and see continents and oceans. The very first Earth-like planet image is going to be like this, a pixel smeared on a CCD. So I was just recently this weekend in Tucson at an event hosted by a Research Corporation for Science Advancement called SciLog. And they have SciLogs on different topics, but this one was signatures of life in the universe. And so the idea is, can we come up with ideas for how to find life elsewhere? There are folks who are looking for life in situ in the solar system, and folks like me who are thinking about the remote signatures of life. One thing we can notice when doing that is taking Earth as an example. Life has had an indelible influence on our own atmosphere. This is a plot that's showing the production of different gases on Earth today and on a hypothetical Earth without any life on it. And you can see just how different those histograms here are, right? We're seeing very little oxygen and much lower methane and nitrous oxide on this planet without life compared to Earth, which has life. And so we can think of potential biosignatures. So one is maybe gaseous products of life. So I mentioned oxygen. Photosynthesis produces oxygen. Oxygenic photosynthesis produces oxygen as a waste product. Oxygen has infrared spectral features, which if we found them on an exoplanet would be very interesting. A photochemical product of oxygen is ozone, very helpful for us because otherwise the surface of Earth would be uninhabitable for us because of the ultraviolet radiation. But ozone also has spectral features that could be inferred from remote observation. And surface signatures. So there's something called the vegetation red edge, which on Earth is used to map vegetation. And this is the idea that vegetation becomes very reflective in the infrared compared to the visible, where chlorophyll is absorbing. So we can map vegetation on Earth with this simple ratio. And if it were extensive enough on an exoplanet, perhaps we could also find something like that. Pigments, other pigments have their own unique signatures. And of course, both those things vary as a function of season on Earth, which is yet another temporal possibly component to biosignatures. I at one point consulted with National Geographic on a picture they had of a planet with a hypothetical rhodopsin-based phototrophic metabolism dominating the oceans. And so this is a way of capturing light energy through a process that is similar but different to photosynthesis and exists in organisms in hypersaline ponds on Earth. So if we look at Earth's spectrum, and this is obtained from Earth-shine observations, that is light that's reflected off the moon and then collected by ground-based telescopes on Earth. And then you can take out some of the contamination you get from the surface of the moon and you get Earth's spectrum. And so from the spectrum and from the features in that spectrum, you can derive the atmospheric composition, including the oxygen produced by plants, the ozone, that's a photochemical product of that oxygen, the carbon dioxide, that's a result of volcanic activity, the methane, that's also a result of life, the water vapor, which could hint at habitability, and even this vegetation jump that could indicate the presence of land plants. All of that is embedded information in Earth's spectrum. Okay, and that's the kind of thing we want to look for on an exoplanet. Now, I haven't talked about the reflected light. That's reflected light. What we want to look at from a perspective of an observation like is being done with Webb is the transmitted spectrum of an Earth-like atmosphere. And so this is what that would look like. The Earth is different sizes because of the absorption by different molecules in the atmosphere, and we could potentially get an idea of the ozone, water, methane, or carbon dioxide abundance on Earth. There's really only one system right now where we could potentially do that, and it's the TRAPPIST-1 system. Why? It's because it's close. It's the closest system of planets, rocky planets in the habitable zone that transit their star. Not necessarily, and probably not, and almost assuredly not, the closest potentially habitable planets. But remember that transits, most planets don't transit. They just have to be perfectly aligned through random chance from our perspective, such that they are passing between us and their host star. So TRAPPIST fits that bill. And it has multiple planets that may lie within the so-called habitable zone. So D, which is really close, maybe between, it gets about an energy, a level of energy that's between what Venus and Earth receives. So maybe it's like Venus, maybe it's not. E, which is most similar to Earth. F, which is a bit cooler. And G, which is even cooler than that. But we have some unanswered questions that are going to be really crucial if we're going to find biosignatures. So before we can think about biosignatures, we have to think, do they have atmospheres? And that's why these observations of close-in M-dwarf planets are going to be so critical. If they don't have atmospheres, it's going to be hard to justify using all these transits to characterize the TRAPPIST atmospheres. If they do have atmospheres, do they have life? You know, it depends on how common life is in the universe, right? We don't know that. We don't know the probability of life arising. And so that's a problem. But these kind of observations are going to tell us about that. If we find life on the first planet that we look at, it means that life is really, really common. That would be helpful to know. If life is present, it might not be detectable, right? Chemotropes, just living, barely surviving at hydrothermal vents on this planet, they're not going to produce the copious amount of gases in the atmosphere necessary for spectral detection. Okay, so there's so many unknowns, but we don't want to give up just yet. The stellar context is important, and I mentioned how photochemistry is important. If you take the same amount of production of, say, methane in our oxygen-rich atmosphere, and you just put Earth around TRAPPIST, you get 1,000 times as much methane because of the type of spectrum it has and its ability to create the radical species that ultimately destroy methane in the atmosphere. And so one possible biosignature we might look at is this CO2 methane disequilibrium signature. These are two very different oxidation states of carbon and could possibly indicate the presence of life. I also wanted to jump in there and say, you know, this is one of the reasons why it's hard. Methane is present in 5 of the, abiotic methane is present in 5 of the 8 substantial planets with substantial atmospheres in the solar system. Maybe Mars, there's an asterisk there. Earth, it's primarily biological. There's another molecule on Earth that's a potent greenhouse gas and also overwhelmingly produced by life on our planet, and that's nitrous oxide, or laughing gas. And so one of my colleagues and I had this idea, how much nitrous oxide could you make on an Earth-like planet? We used a sequence of biogeochemical models to think about the nitrogen cycle. There are a lot of biology details in here that I might not get through, but the idea is, you know, if you take the amount of nitrogen that's being processed, a lot of it is not being released as nitrous oxide. If you adjust that dial a bit, you could potentially get hundreds of times more nitrous oxide than our biosphere produces. And you add on to that this photochemical difference. The spectrum of the M-dwarf stars is different than our sun. And the overlap of the dissociation cross-sections of the nitrous oxide molecule are such that you would, again, build up a lot more nitrous oxide at a given flux. And so we did these photochemical calculations comparing Earth to other stars and found this favorable production or favorable retention of nitrous oxide for the cooler, dimmer stars. And that effect can be, you know, factors of 10 or 100. If we consider TRAPPIST-1, it's possible that you could get a detectable amount of nitrous oxide if we had more, of course, much more than a little bit more than Earth, but within the realm of possibility according to our modeling. And that would be a really wonderful biosignature: nitrous oxide, methane, and CO2. That biosignature combination would be very intriguing. Maybe you couldn't say with 100% certainty that planet had life, but it certainly has very interesting chemistry going on. And so kind of what we said is, hey, don't give up on N2O as a biosignature. We should look for it. It's plausibly detectable on TRAPPIST-1, and certainly for planets that are other planets that we're going to look for with future more powerful observatories. One of those, and I'm pretty close to finishing here, is called LIFE, or the Large Interferometer for Exoplanets, and that is an ESA mission. And it's a concept of putting a bunch of infrared telescopes in space and using interferometry to image in the mid-infrared the emitted light from temperate planets. That's not something that JWST can give us because of the contrast between the star and the planet and the signal-to-noise limitations. But if we did this, we could potentially find planets and characterize their atmospheres, find ozone, methane, and nitrous oxide, which would again be a very, very amazing biosignature. The National Academy of Sciences just recently promoted this idea of the Habitable Worlds Observatory. This would be a telescope that would look at reflected light. Okay, so in the ultraviolet, optical, and near infrared, the kind of light that bounces off our atmosphere, gets scattered off our atmosphere and reflects off our surface, the kind of light that we can see. And this is a model image of a hypothetical solar system twin, 10 parsecs, which is about 30 light years away, and what it would see if it looked at our solar system. And so you can see Venus, Earth, and Jupiter here. And if you put that Earth through a spectrograph, you could get that spectrum that I showed, the Earthshine spectrum with oxygen and methane and carbon dioxide in it. This was recommended by the 2020 Astronomy and Astrophysics Decadal Survey. And the mandate is to have a telescope capable of characterizing 25 temperate planets around stars in the solar neighborhood. Most of those planets are, probably all of them are unknown as of yet because they don't transit, but they might be there. We know from statistics that we've gained from TESS and Kepler that they're probably there. And then finally, one really intriguing thing, I don't want to completely leave this out. We've been talking about biosignatures, evidence for simple life, microbial life really, but what about technosignatures? What about evidence of technological life? I was part of a recent review that considered this and thought, hey, I mean, even if our chances of finding these signatures are small, they would be worth looking for. Their specificity, that is, their attribution to life, is a lot stronger than maybe some of these biosignatures would be. And this is a concept image that was actually produced by UC Riverside by a graphic artist named Sohail Wasif. I basically commissioned him to make this and described what I wanted. And what this is showing is, the kind of technosignatures we may find from an alien civilization: radio, optical, laser pulses, perhaps. There's a program called Optical SETI that is looking for such laser flashes. What's really important here is that if you have a narrow wavelength range for your laser, that laser can outshine the star at that wavelength with relatively little energy compared to the energy from the star. And then looking for artificial molecules in the atmosphere. So sulfur hexafluoride is almost entirely industrially produced on Earth as an insulator. And that kind of molecule would not exist at high abundance in an exoplanet without industry. And so maybe that is something we also look out for. And then just a plug for my colleague Stephen Kane, who's going to be speaking next time about planetary habitability and connecting Venus's past with Earth's future. He's also a big proponent, the originator of the Venus zone concept, and very deeply involved in detecting and characterizing exoplanets, including these Venus-like exoplanets. So with that, I'm just going to end and say JWST is providing this unprecedented insight into exoplanets. We're going to learn more in the next 2 to 3 years than we've ever known about rocky exoplanets. And this is bringing us closer to the search for habitable and inhabited planets elsewhere. Thank you.
That was excellent. Thank you so much. And we'll take questions from you in the audience. So come over to you with a microphone. And if you could talk into the microphone when you have questions so that it can be on the Zoom recording.
Very interesting. Thank you very much. Given the amount of time it takes for the light to get here, even when you're looking at it with a Webb,
Yep.
are you looking at the properties as they are today or they were?
You're looking at them as they were, but yes, so that's a good question. Light has a finite speed. And so for example, that rocky planet I showed you, that's 99% of Earth's radius, is about 41 light years away. So we're seeing the planet as it was 41 years ago, right? And so we're limited by that. Most of these planets, of course, in order to get the signal to noise, to get good information about their atmospheres, they have to be within a few hundred light years. So geologically speaking, it's very recent. Yeah.
I'm back here.
Hi.
Way at the back. See?
I see you.
This morning, I read an item that there's some evidence, or at least speculation, that on Venus, there is active volcanic eruptions.
Mm-hmm.
If that is the case, and you may want to comment on this, or perhaps a question for Professor Kane, how would that affect the atmosphere and chemistry of the planet?
Yeah, so the question is, there's this idea, there's a recent discovery of potential volcanic activity on Venus. How would it affect its atmosphere? And this is really interesting stuff. So it's actually looking at archival images of Venus's surface and noticing this difference that may be attributable to lava flows. And it's still in its early stages, and you know how some of these things go, where there's a claim made, and then it turns out, oh wait, there's a mistake made, or it's something else. But we kind of do expect that Venus has had a volcanic activity. It has sulfur dioxide in its atmosphere, which is a product of volcanism, of volcanic activity. And so one of the big mysteries has always been, where does the sulfur dioxide come from if there's no volcanic activity? And so this could actually help answer that question. What is creating this gas? What is maintaining it?
Excellent presentation, thank you. To the extent this isn't a hopelessly obsolete question, there was a time when Drake's equation meant something significant.
Yeah.
Does it still, and is your work making it seem like it's still reasonably accurate?
Yeah. So Drake equation. So I showed you Drake's equation last time, 2020. I spoke here. It was a little bit of a different focus on habitable and inhabited planets and more biosignatures. But Drake's equation is a way to estimate the number of communicating civilizations in the galaxy, the kind that we may detect through radio observations. And what's really amazing is that Drake only had one term when he made his equation, which is like the star formation, number of stars in the galaxy and the star formation rate. Now, actually, we know more parameters. So we know the fraction of stellar systems with planets. It's like all of them on average. We know the fraction, we're getting more information about the number of planets per star system. And we're even getting statistics about the number of planets in the temperate zone, so in the potentially habitable zone. Now, in Drake's equation, that would be the fraction of planets that are conducive to life. However, it's not quite true that the number of planets that are in this temperate zone are exactly equivalent to the number that are suitable for life, right? Because there are other ingredients besides just the amount of radiation that the planet receives in its size. But we know a lot more than in Drake's time. And if we actually get to the point where we can start to characterize biosignatures, that gets us all the way to the fraction of planets with life, right? And then, of course, there's the fraction of planets with life that develop intelligence and fraction of intelligent species that develop civilization and so on, the length of a civilization, which are going to be very hard. But I think that we're in the regime where we are getting deeper and deeper into the Drake equation with real data. Thank you.
Making you do all the running around.
I was wondering if you're developing this great model on transmission spectrums of Earth and the biosignatures of Earth, and you keep working that way, could you develop a model that an AI could use to scan the data of the Webb much more quickly and then only ping you when it sees something significant, and thereby increase the number of interesting planets that you actually spend your time on?
Right, yeah. So can you make an AI that can effectively detect anomalies that could be associated with biosignatures? So I think that ultimately we want to get to the point where we're getting so much data that we need an AI. I think right now, Webb, the data are still sparse enough that people are looking at each and every spectrum as it comes in. And so what we want to do is build an ensemble of spectral data that where that would be important. AI is being used to find planets, so it's looking at the Kepler database, it's looking at the TESS database, and it's finding planets that people hadn't found before by looking for patterns. And yeah, biosignatures. The thing about training AI to do it, and it's a good idea, is that it's ultimately limited by the training set. And so if there's some anomaly that's not in the training set, it might be, or it can identify the thing that's not in the training set. Yeah. Right.
That was a really good question. Thank you for that.
Excellent, wonderful presentation. I'm so excited by all this new data. But the parallel thing of looking for, what was it, SETI, the search for extraterrestrial life,
Yeah.
that big thing they used down in Puerto Rico collapse was a big, is there any, are they still looking for radio kind of signals, or can Webb do that as well? I didn't think Webb dealt with radio waves.
Right, thanks. So the question is about SETI, Webb's role, and yeah, the Arecibo radio telescope unfortunately collapsed, and we can no longer use it. There's actually a radio telescope that's much bigger in China that's being used to look for radio waves. And there's a Van Allen telescope array here in California that's being used to look for radio waves. Radio is not the wavelength regime that James Webb is sensitive to. It's sensitive to the infrared. That's not to say that there can't be some technosignature that maybe James Webb would be sensitive to. I'm sure that as time goes on, people are going to be mining that data set for anomalies that could be biosignature, probably not biosignatures on the plants we're looking for, but maybe even technosignatures.
Any other questions for Dr. Sweeterman? One over there. Okay, Nancy's got you.
Well, this is really basic question. Can you just give a really short explanation of a biosignature? Is it because of a certain wavelength, you now know there's a certain molecule in there?
Yeah, so you've got a lot of it. So we're looking for the evidence that a molecule exists in an atmosphere based on the spectral signature. But it's more than that, it's the context, right? Because all these small molecules can be made abiotically. It's the idea that in order to get this molecule, you have to have this enormous production of it in the atmosphere. You wouldn't have that much there unless there's this enormous production that's maybe explained by this robust photosynthetic biosphere. On Earth, that's the case. We have this, almost every molecule in our atmosphere has been through life, has been processed by life. Even the nitrogen, even the carbon dioxide, it gets processed through life much more frequently than through geologic processes. And so to see oxygen and methane and nitrous oxide together is very compelling evidence for a biosphere.